All right, so this problem is pretty challenging, but really we can do it instead of writing a full proof here. Let's go ahead and just talk about what we know about this for sure. So they're all three of these quadrilaterals are going to be squares. So I can go ahead and mark all those things as being congruent in terms of the sides, because we know that's the definition of a square, one of the properties of a square. So we also know that in a square, all of the vertices are going to be 90 degrees. So I'm going to go ahead and mark all of those in, at least the ones that are touching that equilateral triangle. It also tells us that the triangle in the inside BEH is going to be an equilateral triangle, which means that each of the measures of the interior angles is going to be 60 degrees, which means that in this case right here, we're trying to prove eventually that AE, DH, and BG, so those are those long sides here, and here are congruent. So really what I'm going to try to do here is to take a look at triangle ABE and triangle DEH, and what's the other one, BHG, and prove that those three triangles are congruent. Right away, I already have two sides congruent in each of them. They also share this 90-degree angle, and we know that this angle right here is congruent to this one, is congruent to this, and those are all 60 degrees, which means that angle ABE is 150 degrees, 60 plus 90. So that means that we have side, angle, side, proving these three triangles congruent. So the proof itself is going to be a lot more challenging than that, just because there's a lot of work that goes into it, but that's the basic idea that goes along with this thing. Now, as long as you can reason your way through it, that's awesome. I'm not expecting a full two-column proof out of this. There's other things we need to focus on, but I think it's an interesting problem. Hope that helped.